So we moved section 7.4 to this week. So if you have worked on it, read it, that's perfect. But you have more time with 7.2 and 7.3 for last homework. And again, if you're late on the homework, you didn't get it done, please make sure you submit it as a comment and explain why you were late. And I will always consider those. I'm not saying for full score, but at least I will consider them. So it's better late than never. Please make sure you submit them and you go through them sequentially, get them done. But this week you're having to talk about 7.4, 7.5, and 7.6. Now 7.5 and 7.6 is a discussion of general strategies in integration. Basically, it says, okay, just here is an integral. All the things you learned from 7.1 through 7.4, use them to solve this. So that's what it is. Like there's no real lecture for it. So my videos for 7.5, 7.6 would be just basically going through some integrals from the homework on that topic. And of course, 7.6 is the table of integration, which uses the back of the book. We don't really focus too much on it because if you're going to go to the table, then you could probably, it will be something that you can figure it out to some extent. But I'll still look at some examples of how to use a table just to comfort you. But at the same time, it's not a big part of the test. It's not going to be a big part of the class. It's more or less saying that, you know, if you get stuck or if the integration process takes too long, you can use a table to make it shorter, like faster. There's already a formula that would help you to integrate. So really the only new topic this week is 7.4, which I hope is not new, as you hopefully seen it as you were reviewing for this. In 7.4, we're trying to answer a question like this. What happens if I have an integral of 1 over x plus 2 times x plus 3? Now, this could be a result of me having integrated it already, having factored it already in the bottom, or it could be just the problems given to me like this, something like this. And things similar to this. It could be like x plus 2 squared or x plus 3 cubed or x times x plus 2, x plus 3, something like that. It could be many combinations down here. And there could be many things on top. And we'll talk about how to handle each of those. But this is, in a simple form, this is what I'm trying to answer. Now, if somebody did not take this class and you give them something like this, they're like, oh, sure, I can write it as 1 over x plus 2 times 1 over x plus 3, done. But you guys know, I mean, integral of 1 over x plus 2 times integral of 1 over x plus 3, they will say something like this. And that's not correct. That's not correct. You cannot do that. Integral of f times g is not equal to integral of f, integral of g. We talked about that when we were talking about the initial discussion of integration. It doesn't work that way. So what should we do? Well, if I could express it as a sum of two fractions, and the fractions had nice denominators, namely the two factors, then maybe that would be very nice, right? Then I could use the natural log as an antiderivative. It would be very good. This process to go from this to this is called partial fraction decomposition, PFD. Now, the process is a pretty methodical, pretty well-established process. And I'm going to explain to you guys different cases and how to do the partial fraction decomposition. But you're really trying to do something like this. This is the goal. This is the end result. And then, of course, for this, I know that the numerators will be a and b, just numbers. So let's do this on the side. We have 1 over x plus 2, x plus 3. And again, this is a very simple example, but it's a good starting point. Is a over x plus 2, b over x plus 3. I'm going to take the common denominator on the right-hand side, so it looks like the left-hand side. So I get x plus 2 times x plus 3. And then I get a x plus 2 plus 3 if I take the common denominator, b x plus 2. Again, remember, you're following the correct taking the common denominator process. You don't always get to multiply a by x plus 3 and b times x plus 2. You will see that the common denominator is the least common denominator. I don't want to make it more complicated now, but remember that it's a fully process of taking the common denominator, okay? And then 1 over x plus 2 times x plus 3. If the denominators are the same, so the numerators would have to be the same. So 1 is equal to a x plus 3 plus b x plus 2. Okay, so that's the idea. Now, there's a couple ways you can go about doing this. One way, which is a very, very standard way of looking at this, you distribute A, distribute B, factor out the X from AX and BX term, factor out, don't factor, just combine the numeric part, and tell yourself, well, the number has to match on both sides, and the leading coefficient, the coefficient of the X, which in this case is 0x, should match. So A plus B would have to be 0, and 3A plus 2B would have to be 1. So from here, you get A is negative B. Plug it in here, you get 3 negative B plus 2B equal to 1, or B is equal to negative 1, which as a result, A would have to be 1. So this becomes 1 over x plus 2 plus negative 1 over x plus 3. Now you can split it because addition works well with the integration. It splits. Then this is just the u. If I use substitution, so this would be u, and of course du is equal to dx. Let's call this v, and dv is equal to dx. So this becomes 1 over u du, 1 over v dv. So it's natural log of u, natural log of v, plus some c that comes from both of them. And then it's going to be natural log of x plus 2 minus natural log of x plus 3 plus c. If you really wanted to, you could combine those two as natural log of x plus 2 over x plus 3 plus c. And that's your antiderivative. If the numerator looks something different, if the numerator was not this, the numerator was not 1, it was, say, it was something else like 2x plus 5 or something like that. It doesn't really change much. It's just the calculation here would be different. Now, let me do this calculation slightly differently. Let me do this process of finding A and B slightly differently. So let's go back to what I had was 1 equal to A, x plus 3 plus B, x plus 2. What I did here is totally fine. You can do it this way, and it works, actually works faster for some problems than what I'm going to do next. But what I'm doing here works a lot faster for many more problems that we're going to be working with. So it's called the Heaviside method. Basically, what it says is the two sides would have to be the same, and Heaviside is, of course, not side, it's the name of the person. And the two sides would have to be the same for every choice of x. So why don't we pick our x's carefully? Suppose x is equal to negative 3. So I get 1 is equal to A, negative 3 plus 3 plus B, negative 3 plus 2. So it's going to be 0A, and that's why I picked negative 3, negative B. So B turns out to be negative 1. And then I'm going to pick another x carefully. I'm going to pick negative 2 as my x. And then I get 1 equal to A, negative 2 plus 3 plus B, again, negative 2 plus 2. Picked it carefully, so this is going to be 0. So I get A is equal to 1. Everything else works out the same way. So in a way, you pick correct values of x, or the type of values of x that will eliminate one or more of the variables, and normally just gives you the one you're looking for. Sometimes you cannot do that. You'll end up with 1 or 2, maybe. And then you're going to set up system of equations for solving those. But still, your system would be a lot less complicated than what you would get if you do it differently. Okay. So going to back to this again, if I had something like, say, 2x plus 5 over x cubed minus 5x squared, what did I use last time? Okay, minus 6x dx, you get something like this. There is a temptation to do a u sub at the bottom and look for your du at the top. The problem is you don't have the du you're looking for on the top, because if you do use substitution here, you get 3x squared minus 10x plus minus 6. You don't have that on the top. So u sub, although tempting, is not going to work very well. However, I have to let you know that some problems, u sub is the way to go. You don't want to do partial fraction for that part. So now I can notice the denominator, if I factor it out, is x times x, oh, sorry, plus 6. X times x minus 3, x minus 2. Dx. Once again, I'm sensing partial fraction decomposition. I'm going to say, okay, then this is going to be a over x, b over x minus 3, c over x minus 2. And I'll tell you why I choose a, b, and c in the next example. So this is going to be equal to 2x plus 5 over x, x minus 3, x minus 2. Okay, so I'm going to get a common denominator on the right-hand side. So this already has an x, so the common denominator is going to be x, x minus 3, x minus 2, what we have on the left. So a already has an x, so that part, it needs the rest of it, so x minus 3, x minus 2. B already has an x minus 3, so needs an x and an x minus 2. C already has an x minus 2, needs an x and an x minus 3. Then I'm going to set these two sides equal to each other. Right? So I'm going to set 2x plus 5 equal to a, x minus 3, x minus 2, bx, x minus 2, cx, x minus 3. Yeah. Now I'm going to choose the x's carefully. Let's say, suppose x is 0. That's an easy one, right? So I get 5 is equal to a negative 3 times negative 2 because x is 0. But bx is going to go to 0 and cx is going to be 0. So I get negative 6a is equal, positive 6a, sorry, is equal to 5, which means a is equal to 5, 6. Now I'm going to pick x be 2 because you see I have a negative 2 here, minus 2, minus 2. So those two cancel out. So I get 2 times 2 is 4 plus 5 is 9. I get 0 here. I get 0 here. And then here I get 2c, 2 minus 3. So I get negative 2c is 9, which means c is negative 9 half. And then I'm going to let another x to be maybe 3 in this case. 2 times 3 is 6 plus 5, 11. 0. 3 times b, 3 times 2, and 3 minus 2. So from here, I get 3b is equal to 11, or b is equal to 11/3. So my partial fraction gives me a, which is 5/6, b, which is 11/3, c, that's negative 9/2. Right? So if I'm integrating this, I'm also integrating this. Right? And then, of course, the integration process would not be too bad because then I have 5/6 integral of 1 over x plus 11/3 integral of 1 over x minus 3 plus negative 9/2 integral of 1 over x minus 2. So 5/6 ln of x plus 11/3 ln of x minus 3 minus 9/2 ln of x minus. I don't know if you want to really plus c, of course. I don't know if you want to combine them, but they won't combine nicely. So I would choose not to do that for this problem. Okay. Now, yeah. Now let me go ahead and give you the rules of partial fraction decomposition. What are the things you have to do? What are the numerators that you pick for different choices of denominators? So if you have a denominator that looks like a linear factor, now it could be to any power. The power is not important. But if your denominator is a linear factor to any power, the numerator is going to be a number only. Okay? If you have a denominator that's to any power, the numerator would be a number only. If you have a denominator that's what we call irreducible quadratic, which means you're a quadratic that doesn't have any real solutions, like x squared plus 4. If you try to solve for x, if it's equal to 0, if I solve for x, I get a complex number, 2i, or negative 2i. So no, this doesn't have a real solution. Then the numerator would be in the form of ax plus b, cx plus d, dx plus e, or whatever. Okay. Now, if you have different powers, so if I had, say, 2x plus 5 over x squared times x minus 1 cubed, and I want to set up a partial fraction decomposition for this, it's not just going to be something over x squared, something over x minus 1 cubed. No, it's going to be something over x and something over x squared, something over x minus 1, something over x minus 1 squared, something over x minus 1 cubed. And since they're all of this form, there's going to be just numbers on top. So whenever you have a certain power, then you have to consider everything from 1 to that power. So x to the 1 and x to the 2, x minus 1 to the 1, x minus 1 to the 2, x minus 1 to the 3. If it was a fourth power here, then you go all the way to 4. Okay. So that's how you're supposed to set it up. Now, yes, I know sometimes like A and C and D will turn out to be 0. And you do get just B and E. But that doesn't mean that's a common rule. That doesn't mean that's a general rule. That doesn't mean that's how you're supposed to always do this. It just happened that that's the case. It doesn't bother the students. They're like, well, I did all this work and it just turned out that A, C, and D are 0. And had I just done it without those, like just assume B over x squared and E over x minus 1 cubed, I would have still get done. But I didn't, and I did all this, and I end up with having those to be 0. It just, that was a coincidence. That was a coincidence. The more you do this, the more feel you get when you're going to have a case where you're going to get zeros for your numerator. But you can't assume that. You have to still go through the process for that. Okay. So yeah, it could get a little bit messy. I understand that, but it is, as I say, within your ability at the time you're going to have for the test or such. Let me do one of the homework problems actually. Let's do x squared plus x plus 1. So let's integrate from 0 to 1. This is number 19 from 7.4. 0 to 1. It just caught my eye. So it seems to be a nice problem. So this is what I was talking about when you have powers. So my partial, and here's what I'm going to do. I'm going to do a partial fraction decomposition on the side, and then I'm going to go in there and I'm going to plug it in and I'm going to integrate. Okay, so let's just do it on the side, see what happens. So I have x squared plus x plus 1 on the numerator of the original expression. Then I'm going to write the number of denominators, one for this and the second one for this, and then one for that. So x plus 1 squared, and x plus 2. And remember, if it's anything to a power, it doesn't matter. As long as it's a linear combination to a power, then it's just going to be a number at the top. We'll also do a problem like this as well. So this one is good for the power case. And I can also remind you guys of how the common denominator actually works for these. So I get x squared plus x plus 1 over x plus 1 squared, x plus 2. And my common denominator must be x plus 1 squared, x plus 2. That's by construction. The way you pick these, it has to give you that as a common denominator. But notice this is the least common denominator. I didn't just multiply this by this by this. Otherwise, I would get it to the third power, and I just got to square power. Square seems to be enough. Okay, and here's the part that you have to pay attention to. When you try to do the numerator for a part, it's not going to be a times this times this. No, a already has one of these. So even though it's x plus 1 squared, you already have a 1x plus 1. So you need one more x plus 1 to match, and then x plus 2. So now I just multiply the numerator of this by x plus 1, x plus 2, and the denominator by x plus 1 plus x plus 2, then I get this denominator. So when you get a common denominator, you don't just blindly multiply the number by the other remaining denominators. No, you have to see what I already have, take that out of this denominator, and just multiply a by what's left from that list. For b, I already have x plus 1 squared part, so I only need an x plus 2. Very good. And for c, I already have an x plus 2, so I only need an x plus 1 squared. See how it works? Very good. Now I'm going to, of course, just set the numerators equal to each other. X squared plus x plus 1 equals to a, x plus 1, x plus 2, b, x plus 2, c, x plus 1 squared. Now, once again, you could distribute and then you can cancel things as much as you want, or you can use the Heaviside method. So let's just do that. Let's pick -1 for x. So I get -1 squared, which is 1, minus 1 plus 1. -1 for x, this part would be 0. This part would be -1 plus 2, which is 1b. And this one would be 0. So b already I know is 1. Now I'm going to pick -2. -2 squared is 4 minus 2 plus 1. This part would be 0. This part would be 0. And then I get -2 plus 1, which is -1 squared is 1. It's c. So c turns out to be -2. And that's what I was talking about. They don't always give you the final answer, because no matter what I pick for a now, for numbers, I cannot get a by itself, because whatever makes b part 0 also makes a 0. Whatever makes a c part 0 also makes a 0. So really, I don't have much of a choice there. But I don't have to pick those numbers. I can just pick any other number. Let's just pick 0. 0 is equal to, 1 is equal to, 0 plus 1 is 1, 0 plus 2 is 2, 2 times 1 is 2, 0 plus 2 is 2, 0 plus 1 is 1. But I already know b, 2 times 1, and I know c. So a becomes 1/2. Oh, sorry. C is equal to 3. Sorry. I don't know why I said c is equal to -. Oh, I see why I said that. Yeah, sorry. C is equal to 3. So if c is equal to 3 here, thanks for the erasable pen. So z would be 3, and then 2a, plus 2b, which is b is 1, so 2 plus 3, which is your c, is equal to 1. So 5, it's going to be 5 plus 2a is 1. Take 5 to the other side, becomes -5, plus 1 is -4. 2a is -4, or a is -2. Yeah, that was a good catch there. Okay, so a is -2, b is 1, and c is 3. So with that 0, I just pick a number that was easy to calculate for me. I usually pick 1, -1, 0, whatever. But 2 and -2 was intentional because I want to make sure that some of those parentheses are 0 with that choice. Okay, so now, yeah, very good. So now I get 0 to 1, -2 over x plus 1, 1 over x plus 1, very good, squared, plus 3 over x plus 2. Very good. Now the first one is easy. It's just -2 natural log of x plus 1. Very good. And I evaluate that from 0 to 1. Very good. Second one is 1 over something squared. Is if I do a u substitution, I just get -1 over x plus 1 from 0 to 1. You can take the derivative of it, you end up with that. Take the derivative of x plus 1 in the denominator, you get Negative comes down, which cancels with this negative, you get x plus 1 to the negative second power. That's this. So antiderivative of this is this. You could use a u substitution if it comforts you. Plus 3 natural log of x plus 2 from 0 to 1. No plus c because it's a definite integral. Negative 2 natural log of 1 plus 1, natural log of 0 plus 1. 1 over 1 plus 1 minus 1 over 0 plus 1. 3 natural log of 1 plus 2, which is 3. I'm kind of space away right now. So 3 minus natural log of 0 plus 2, which is 2. So it's going to be negative 2. Natural log of 1 is 0. So negative 2 natural log of 2. This is 1/2 minus 1, which is negative 1/2, with the negative is positive 1/2. Plus 3 natural log of 3 minus 3 natural log of 2. You could again try to combine them and clean it up a little bit, especially the last two. But actually right now you could cancel these two together. So I get a negative 5 natural log, oh, combine, I'm sorry. Plus 3 natural log of 3 plus 1/2. That would be just fine. That would be a good answer. Let me do number 23. 23 is the, that number 23 is good. That one is actually the quadratic, the irreducible quadratic I was talking about. So let's do 23. Okay. Again, when you do these problems, I hope you slow down the video sometimes. I hope you pause and you look at it, take another set of notes for yourself. And if there's something about this in the video, you're like, I'm not sure what he's doing or why is he doing this. I keep these videos, of course. And you can just reach back and just send me a message or come to office hours, Tuesday, Thursdays, 2 to 4, or just comment on this or whatever. And I'll be happy to clarify things for you if you want. If there are some errors in the videos, that would be nice for you to bring it up. Say, hey, this part of the video is not quite right, which I hope that's not the case. But if it is, please bring it to my attention. So let's do 23 together. This is probably a good problem for us to look at. It's 10 over. This is number 23, yeah, in 7.4. 10 over x minus 1, x squared plus 9. Yeah, that's the irreducible quadratic I was talking about. Because you can't really factor x squared plus 9. If you try to solve for x, you get plus or minus 3i, because the square root of negative 9 is 3i. The imaginary number, complex number, so we can't really do much with that. So my partial fraction decomposition would be 10 over x minus 1, x squared plus 9 would be something for x minus 1 and something for x squared plus 9. But that something for x squared plus 9 is bx plus c. Remember, every time I have irreducible quadratic in the bottom, the top would have to be ax plus c, b plus bx plus c, whatever. It has to be a linear term. So let's get the common denominator. Once again, my denominators match, so the numerators would have to be the same. Whenever I'm dealing with irreducible quadratic, it just seems it's better for me to just distribute everything and then set like terms equal to each other. It just seems like it. I could still plug in x equal to 0, x equal to 1, just try to make it work a little bit. But like if I plug in x equal to 1, this part goes away, then I get 10a is equal to 10, a would be 1. I could do that. Or I could just distribute and clean it up. Or you could do combination of both. You can do a combination. That's no problem. So I could say x equal to 1, 10 is equal to a 1 plus 9. And then this part is just going to be 0 because 1 minus 1 is 0. So I get 10a is 10, which means a is equal to 1. So now I found my a. And guess what I'm going to do? I'm not going to pick another number, although I could pick like 2 or 0 or whatever, and set up to figure out what my c and b are. Or now that I know 10 is x squared plus 9 because a is 1 plus bx plus c x minus 1, Then I can just distribute x squared plus 9 plus bx squared minus bx plus cx minus c. So I get 1 plus bx squared plus negative b plus cx plus 9 minus c is equal to 10. So 10 would have to be 9 minus c. So I got my c. And then negative b plus c would have to be 0 because there's no x term on the right-hand side. And I know c is negative 1. So b is negative 1. So I got that. And of course, the last term, b minus 1 plus 1 would be 0 as well. So it works. So b is negative 1. So now my integral becomes very nice. X minus 1 plus negative x minus 1 over x squared plus 9. Okay, so far good. But it seems like I'm not having a same simple situation as before because I have a very interesting integral here that I have to deal with. So, well, let's break it. Right? Now, the first one is easy, natural log of x plus x minus 1, no problem. Second part, I'm going to split it even more. And I just wrote it as a 2 fractions. And you can do that, of course. You're not. You can split over the denominator. That's why we do partial fraction decomposition. Numerators, though, if you're addition of 2, 3 numerators, sure, why not? Split them. Okay. So just to reiterate, if I have a plus b over c, I can write it as a over c plus b over c, no problem. But if I have a over b plus c, it is not a over b plus a over c. So that's not true, but this part is true. And that's what I'm doing here. So be careful. You cannot do that. So still, and then I have a plus c or something at the end. So ln of x minus 1 minus. Here I have to do a u substitution. If u is this, then that means du is 2x dx. I only have x dx, so 1/2 du is x dx. It's a u substitution from section 5.5, if you don't remember. So I'm going to replace x dx with 1/2 du. And this one is a arctangent situation. If you remember, you could do a trig sub here if you really insist on doing this, seeing the steps of the integration. But if you remember your arctangent, this is just a simple arctangent formula. Now, let me remind you what arctangent really looked like. Arctangent used to be if I have integral of 1 over 1 plus x squared is tan inverse of x. So that's the form of an arctangent I have. But here I don't have 1 over 1 plus x squared. I have 1 over x squared plus 9. The difference is I have a 9 instead of having a 1. So you can just do arctangent just directly. You have to do something about it. Now, a lot of students just get enough comfortable with this that they don't write the next steps I'm writing, but I think it doesn't take that many steps to do it. So you could factor out the 1/9. Then this is really and then you let u be x over 3. Du is 1/3 dx. So you get 1/9, 1 over u squared plus 1. And then since I only have dx, I multiply both sides by 3. So I get 3 du. So I get 1/3 1 over u squared plus 1 du, which is 1/3 tan inverse on u plus c. And u, we chose it to be x over 3. So it's going to be 1/3 tan inverse of x over 3 plus c. If you want to write step by step by step by step. But again, you get so comfortable with this that sometimes you don't write that. And then 1 over u is u in this case was x squared plus 9. And of course, this c is a combination of the c's you get from each of the antiderivatives, but I combine them as a single c. Okay. Okay. Now, these situations are all nice because the top has a degree less than the bottom. Numerator has a smaller degree than the bottom. Here, like it's degree 0, the bottom is a 3rd degree, and so forth. So it's like the highest degrees in the bottom. But there are cases where the denominator actually has a lower degree than the numerator. And if that happens, then you have to do what we call long division. I don't know if you guys remember long division from your algebra classes. Let's do problem number 15, which is like that. So again, this is a case where the numerator has a smaller degree than the denominator. I'm sorry, has a larger degree than the denominator. So this is 7.4, number 15. -1 to 0. X cubed minus 4x plus 1. X squared minus 3x plus 2. Notice the top is degree 3, the bottom is degree 2. So what we do is we call long division, which means you divide x cubed, and I'm going to write all the terms, 0x squared minus 4x plus 1, divided by x squared minus 3x plus 2. X squared and x cubed, x times. So you get x times x squared is x cubed. X times 3x is negative 3x squared. That's why I put a placeholder for x squared. X times 2 is 2x. Just like long division of numbers. So make sure you have placeholder for all the powers of x going from the highest to the lowest. Then you look at the first term of the both divisor and dividend. And then you say, okay, x squared goes into x cubed how many times? Or in a way saying x cubed divided by x squared is what? Is x. X goes here, then you multiply x by everything and write it here. Then you subtract. X cubed minus x cubed is 0. 0x squared plus 3x squared is 3x squared. Negative 4x minus 2x is negative 6x plus 1. 1 comes down. Then I can repeat the question. X squared into 3x squared how many times? 3 times. 3x squared minus 9x plus 6. I subtract. These parts cancel out. I get 3x minus 5. And then that's it. I'll reach a degree lower than this. That means my fraction can be written as the quotient, which is x plus 3, plus the remainder, 3x minus 5, over the divisor, x squared minus 3x plus 2 dx. So after you're done with your the dividing process, then the divisor, dividend over divisor is going to be equal to the quotient plus remainder over divisor. Okay. The top, this is the original top, right? This is the original denominator or bottom. Is the quotient, that's the remainder is what you end up with here, and then divisor still is the original bottom. Same thing as numbers. Numbers, you do the same thing. Anyway. So I get -1 to 0, x plus 3 And then -1 to 0 of this part, which I can now factor it. Then I can do a partial fraction decomposition of this. I switched the order just because of the spacing. Then ax minus 1 plus bx minus 2 is 3x minus 5. When x is 0, when x is 1, I get 0 plus negative b is -2, which means b is 2. And then when x is 2, I get a plus 0 is equal to 1, which means a is 1. So this antiderivative, of course, is 1/2 x squared plus 3x. And I evaluate that from -1 to 0. This one is going to be a plus b. Having spacing problem today. So this is, of course, let's just use a clean sheet here. Does everybody feel okay? You can always pause the video if you wanted to, but yeah, everything okay here? I just did the heaviside method here. Yeah, okay. So here now I'm gonna say 1/2 x squared from -1 to 0, 3x from -1 to 0, natural log of x minus 2 from -1 to 0. That's very important to put the absolute value, okay? Plus 2 natural log of x minus 1 from -1 to 0. So it's 1/2 0 squared minus -1 squared. 3 0 minus -1. Natural log of 0 minus 2 minus natural log of -1 minus 2 plus 2 natural log of 0 minus 1 minus 2 natural log of -1 minus 1. Okay, so I get 1 minus 1, so I get -1/2 plus 3 plus natural log of 2 minus natural log of 3. This is going to be 0 because natural log of 1 is 0 minus 2 natural log of 2. That's -1 minus 1 is 2. Okay. Which is going to be equal to, again, natural log of 2. I have 1 here and 1 here. So, and this one is going to be -5. It's going to be 5/2, sorry. 5/2 minus natural log of 2 minus natural log of 3. You have the choice of combining those. I don't know if you want to, but. Which is going to be 5/2 minus natural log of 6. If you again, let's go through that. Okay, if you want to combine it, you don't have to combine. That's a little bit more involved because you have to do the long division. Not everybody likes long division. And then you do partial fraction decomposition, and then you calculate the integrals. But partial fraction decomposition is your friend. It just doesn't seem like it, but it is your friend. Let's do number 26. Let's do number 26. 26 is, I would say, probably a good example to work with when you have irreducible quadratic. Some of these could be very long. You'll see. But some of these could be very long. As you'll see, you have a lot of things you have to worry about sometimes. Again, I'll do partial fraction decomposition on the side, and then I'll combine them together. Because it's a square and it's an irreducible quadratic, my denominator is going to be x squared plus 1 and x squared plus 1 squared. Numerator, because they are irreducible quadratic, would be ax plus b, cx plus d. So it doesn't matter what power of that quadratic it is, it's still going to be, this is problem number what did I say? 26. Yeah. It doesn't matter what power it's going to be, it's still going to be cx plus d, ex plus f, whatever. So the common denominator is going to be x squared plus 1 squared. And this one already has one of them, so I just get ax plus b times x squared plus 1. And then the other one already has everything that it needs, so it's really not much. That's already the denominator. So now I top these two, I'm going to set them equal to each other. We have 4 variables to solve for. A, B, C, and D. So I don't know how you like to do this. You can distribute, collect like terms, see what happens. I think for this type of problem, maybe that's the easiest way of going about it. Let's do that. So ax cubed plus bx squared plus ax plus b plus cx plus d. So ax cubed plus bx squared plus a plus cx plus b plus d. So a obviously has to be 0 because there's no x cubed term on the right. B has to be 1 because the x squared term on this part is 1, so B has to be 1. A plus C would have to be 1 because there's a 1 here and then this is a. And B plus D would have to be 1 because again 1 here and 1, the constant term. A0, B is 1, so if A is 0, then that means C would have to be 1. If B is 1, D would have to be 0. So my partial fraction decomposition of this would be A is 0, so that part is gone. B is 1. C is 1. D is 0, that part is gone. Okay, not too bad. I think it's actually pretty good. The first one, I'm going to split it. I think it's going to be a better choice. Of course, this is arctangent. I can add a C, why not? But yeah, all the C's at the end are going to combine as a different, like a one C for everything. But you can do them as you go, or you can do them separately. Okay. So on this one, I'm going to do a U substitution. I'm going to let U be x squared plus 1, and du is 2x dx, or 1/2 du is x dx. So this becomes 1/2 1 over u squared du, because x dx is, so I get tan inverse x plus c, yeah, sure, plus antiderivative u to the second power in the denominator is negative u to the first power. So it's going to be minus 1/2 1 over u plus maybe another c, c1 and c2. Combine it, why not? So I get tan inverse of x minus 1 over 2 x squared plus 1, because that's what u is. And just plus a c. So that's the c. Combine c1 and c2. Yeah. So if it's irreducible quadratic and you have it as powers, then that's how you handle it. Yeah. I think I covered all different cases of what you could see in the homework or in your future classes. I don't think I skipped any specific type, but if you're doing the homework and you're like, well, this doesn't fit any of the things he has done, and I'm not sure how to go about this, or you look at the solution manual, you're like, oh, they're doing it this, but I'm not quite sure how they're doing it or why they're doing it. Then just come to me or leave me a message, and then I can explain a step or do a problem for you. Not a problem. But as I said, try your hands on the problem similar to the ones I did that I assigned the homework, and I think you should be okay. All right. I hope this helped. And again, communicate with me if you want me to do more problems or other problems.